But good morning, everyone, and thank you for attending the first of the 2025 RIEL seminar series. It's great to have you all here, and I know we have people online. And for the people online, can you please mute your microphones so it doesn't cause any noise disturbances? Hello, welcome. But before I introduce today's speaker, I do have a few housekeeping things to do. Most of you probably already know, but the toilets, if you need to use them, are out this door. It's the same door you came in. Just go out there a few meters, take a left, go outside, open the door, and the toilet's be on the right. Also, in the highly unlikely event of some kind of emergency, follow those same steps, but don't go into the toilets. Go down the stairs and cross this green lawn right here, and there's an assembly point over there. And if you're in doubt, just follow people in front of you. People online, ignore all that. Also, I want to give an acknowledgement to country. I'd like to acknowledge that this seminar is being held on the traditional lands of the Larrakia people and pay our respects to elders past, present, and future. So now I think it's time to introduce today's speaker, Mr. Stephen Tickell. Stephen works as a hydrogeologist for the Northern Territory Department of Water Resources, although it's had many names over the years. Every time there's a new government, the name changes, but we just simply call it Department of Water Resources. And Stephen's been working there for how many years? 20, 25 years?
Since 1990.
Oh gosh, 35 years. So Stephen is probably the most knowledgeable person here in the NT when it comes to groundwater resources. And unfortunately, he's soon to be moving to Adelaide, but he'll still be involved, maybe not physically here in Darwin, but he'll still be involved in the water resources research groups, despite his physical move. And he's also collaborated a lot with various people here at CDU, including Lindsay Hutley, Dylan Irvine, Clement DeVere, myself, and Jenny Davis, and probably some others I haven't even met. So it's a great honor to have you, Stephen. And thank you so much for agreeing to give this talk today. It's an honor. Thank you so much. I'll turn the podium over to you.
Thank you, Bill. It's an honour for me to be invited to speak. It's terrific. So anyway, the subject of my talk is groundwater, the hidden wonder of the Northern Territory. I think groundwater, it's not something a lot of people are aware of, really, because of its nature. It's all under the ground, you can't see it. But really, I think it's an amazing part of the territory environment. It's interconnected with things like vegetation, surface water, soil. So it's an important thing. And I hope by the end of this talk that you also will be of the opinion that it's a hidden wonder of the Northern Territory, even if you've got no idea what it is now. My talk's going to be in two parts. I'll start with just a description of the basics of groundwater, what it is and how it fits in with the hydrologic cycle that most of the Earth's water is part of. And I hope it's not too basic for everyone, but just yell out if it is. Or leave. And the second part of my talk will be about groundwater in the Northern Territory, looking at from a regional picture. So let's go big first. We'll look at the globals, just a few statistics. So 70% of the Earth's covered by water. That's mainly oceans, of course. And the other 3% of the water, let's see what that's composed of. Well, ice and snow, they're the major portion, but I was quite surprised about this. Groundwater is up there with ice and snow. It's quite a huge part of the water environment. And when you compare it with surface water, like lakes, swamps and rivers, it's ordered of magnitude greater. So of that 49%, only 45% of it's fresh. The rest is saline. So fresh groundwater comprises only about 0.8% of the Earth's water. However, in volume, that's about 10 million cubic kilometres. I'm not sure how many swimming pools or that is, but it must be quite a lot. So I mentioned the hydrologic cycle. You're probably all aware of that. It's just the continuous cycling of water between the oceans, the atmosphere, the land, and groundwater is part of that. Some of that water on the land finds its way down into aquifers beneath the ground, and then groundwater moves under the action of gravity and eventually finds its way back either directly to the sea or to rivers, which then go to the sea. So it's an important part of the hydrologic cycle. And the hydrologic cycle, of course, is powered by the sun, you know, causing evaporation and so forth. So I said it's stored in aquifers. What is an aquifer actually? Many people, when they think of underground water, they think of a big space under an empty space that's got water in it under the ground, you know, something like a lake or a cave. But you do get that situation, but it's very rare. Most groundwater is, or most aquifers is solid rock, really, with holes in them, tiny little holes, and of various types. And those holes, they can be up to 30% of the volume of the rock. That's called the porosity. But most aquifers are less than 10% of the volume. So an aquifer is a porous rock that can store water, but also they must be interconnected so the water can flow through it. Otherwise, it wouldn't go anywhere. It would just fill the holes. I'll just go through the different types of openings that make aquifers. Probably the most important one in the Northern Territory are fractured rocks. Like if you look at any rock outcrop or road cutting, you'll see cracks like in this photograph. And they're usually sub-millimetre scale, but they can hold and transmit water. And if there's enough of them, and they're all interconnected, it'll form an aquifer. That's just a schematic thing of what the aquifer might look like. It's just a lot of cracks in the rocks that are, you know, various orientations, and they're interconnected. So fractures have got a number of origins. They can either be tectonic in nature, you know, when the rocks are deformed, when continents bash against each other, or they can also form when rocks or sedimental rocks are deeply buried and they've got a lot of overburden on them, sort of compacting them. And then later on, erosion removes all that material from it, the weight's lifted, and cracks form as the pressure's released. Another important factor with these fractured rock aquifers is weathering of the rock. Now, this is a cross-section of this is a local one. It's near Goldmere Road in Darwin, for those of you who are in Darwin. But the colours in the section represent different rock formations. they're actually very steeply, they're sedimentary rocks, and the beds are steeply dipping, almost vertical. And but see the the zone with diagonal lines, that's the zone where aquifers are best developed. And what it coincides with, the base of that zone, is the base of weathering. So underneath that, the rock's much harder. Any cracks are closed. They're tight, and they generally don't hold much water. And above that zone, the rocks are highly weathered and probably got a lot of clay in them, and which partially blocks the fractures. So the aquifer is actually a sweet spot with depth where the fractures are open and an aquifer can form. The vertical lines are boreholes, and the coloured bits on them are where they intersected water. So nothing sticks to the rules with this sort of thing. So you get some that are shallower than that sweet zone and some that are deeper, but that's just the nature of things. So, and also the blue dotted line at the top, that's the water table. So that's the top of the saturated zone. So the rocks will all be saturated up down to that point, or sorry, up to that point. And notice that the water table sort of parallels the topography. That's quite a common thing where aquifers are what's called unconfined or semi-confined, meaning the water can just go straight down from the surface into it. But you can get the situation where an aquifer's confined, where there's an impermeable layer, and we'll look at some of that later, and water can't get into it. So the second main type of hole occurs in rocks like limestone and dolostone, which are made out of carbonate minerals, and they're relatively soluble in water over geological periods of time. And, you know, you get caves and various sorts of cavities in them. The picture on the right is, it's a picture taken down a borehole in the limestone. And you can see there's holes up to, or they're decimeters in size. So what happens in these rocks is that they're fractured, but as water moves through it, the rocks dissolve and the fractures get enlarged. Now, the third main type is porous rock. We call them, well, porous rock aquifers, we call it, which form in either rock like sandstone, which is made of little sand grains, or just loose sand. And the aquifers form just by the intergranular spaces in the rock. They're the three main types, but of course, as I said, nothing straightforward. You get different combinations of those three types. So with the water cycle, I'll just describe the main parts of that happen to groundwater within that cycle. So groundwater's got a life cycle from when it goes into the ground, we call that recharge. Then when it's in the aquifer, it flows under gravity to lower points in the landscape where it eventually discharges. And this little diagram just gives you an idea how it all works, a simplified version of how it works. Let me go back again. I'll start again. So in the wet season, you get rain and the aquifer fills up to a higher level. And you can see the water table there. I've drawn it so it's parallels the topography. And this is just to give you an idea of how the water moves. Because there's a high point on that hill, the water table's also high, and so some water flows to the left, some to the right. And so you get things called groundwater catchments, the same as you get surface water catchments. Normally they coincide, but in some cases they don't. You can have a groundwater catchment that goes beneath several major surface water catchments. And in this case, the water's flowing to the left to a creek where it's discharging. So when the rain finishes, of course, the water just drains away to the creek until the next rain, and then the cycle continues. Now, this is the worst case scenario. If it never ever rains again, it'll all drain to the level of the outlet, and the water table will be horizontal. But luckily, normally it rains again, up till now. Let's hope it does. Let's look at some of the mechanisms for recharge. A common one is what we call diffuse recharge, where you get rain, widespread rain, and you get more or less water seeping through the soil down into the water table over a wide area. Another type is what we call localised recharge, where surface water is channeled into a point to get into the ground, and that could be in the form of a stream or a lake or perhaps a cave. I've seen a cave down near Cutter Caves where in the wet season you could see a creek just disappearing down a cave. That was interesting. Now, onto discharge. If the water table's below the stream bed, there's potential for recharge, but if it's above it, you can get discharge. Another type is, I call it overflow discharge, where the khaki colour is the aquifer, and the other colour is an impermeable material. So the aquifer is like a bowl, really, and as it fills up, the water has to overflow somewhere, and they're called overflow springs, that sort of discharge. And another type of discharge is, it's an important one here, is evapotranspiration. So where the plants can access the water table, they can use a lot of water. You may get no other type. In the arid zone, you may not see any other type of discharge, any actual water coming out. It will just be through evapotranspiration. And another type is more to do with geological structures. In this case, we've got a bed, which is an aquifer, and it's disrupted by a fault. So water would recharge up the top where that green bed outcrops. That's the recharge area, and it'd flow down. But in this case, the fault is permeable, so there's a pathway for the water to escape. And often you'll find springs along faults, if they're not all faults, but ones that for some reason or other are permeable. So now we'll get on to the more interesting part, I think, is talk about groundwater in the territory on the whole territory-wide scale. So we'll look at where it is and what processes happen. We'll talk about types of aquifers. Can you see that? Yeah. The different types of aquifers and their distributions and properties, like their recharge, discharge, water quality, and how water is used by various things. So let's start with, I shouldn't have used blue. I can hardly see it here. We'll talk about the fractured rock aquifers, which I described before. This is a map of the distribution of it. The dark red colours, the red colours are where you get those aquifers, and they're the most widespread aquifers in the territory. I've divided it into two classes here. The darker red is where there's sufficient fractures, sufficient density of fractures that you can drill in most places and find water. Whereas the light coloured ones, they're rocks like granite, where you've all seen outcrops of granite where you can see big joints in the rocks that between the boulders, but they're usually widely spaced. Whereas in other types of rocks, you know, the joints might be centimetre scale, the distance apart, or maybe metres. So it's in that type of rock, you can actually get a dry. It's not uncommon not to find sufficient water for a water supply. It's not to say there's no water there, but it just may not be sufficient. I've only seen a few examples where bores are drilled and they get nothing but dust coming up. That's relatively rare, but not impossible. So the next type, I've called it fractured and karstic. And karstic just refers to the limestone rocks in a cavernous nature of it. That's just a term for that. And basically the aquifers there are the fractures that are enlarged by solution. So these are the main areas where you find them. The big blob in the middle, that's the Cambrian limestone aquifer, which no doubt most of you have heard about in recent times because of the gas exploration. That's a pretty major sort of aquifer. And it consists of several flow paths. Up in the north, that's that little pointy bit at the top, that's the Daly Basin. And most groundwater there makes its way to the Daly River. Whereas the lobe on the left-hand side, the left bottom, that's called the Wieso Basin. And the water there ends up in the Flora River, which is up here, which then flows into the Daly. The lobe on the right side that goes all the way from Queensland up to Mataranka. Oh, no, it goes to here actually. That water down near Queensland, there's a groundwater divide here, and water to the east of the divide goes to Queensland and ends up at the Lawn Hill area where the rivers there have got beautiful springs. But on the other side of that divide, the water flows all the way, it's hundreds of kilometres up to Mataranka. Although you've got to remember, down here it's quite arid and there's clayey soils, so the amount of water flowing or contributing to flow at Mataranka is quite small from here, even though it's a big area. The gradient of the water table is very low there, so it's not moving fast at all. Most of the water that comes out the Roper River originates, you know, say from Larrimah northwards. other prominent aquifers of this type are around Darwin. It's only a relatively small area compared to the other, but that's the Kulpinia Dollarstone aquifer, and that's the one that supplies part of Darwin's drinking water. And also you've got the Berry Springs Dollarstone.
Oh, I'm on another like a call. No, it's all right. No, all good. No, all good. Oh, I was trying to get it to go away.
Yeah, the Berry Springs Dollarstone's another.
No,
example.
I'm just bear with me.
But anyway, these karstic aquifers are quite important because they have large outflows, and you know all the prominent springs originate from these aquifers. So the last one is our porous rock aquifers, basically sands or sandstones. And the bit that stands out here is in the bottom left corner. That's the Northern Territory gets a little bit of the Great Artesian Basin. The great majority of it's in Queensland and South Australia, New South Wales, but we've got a little bit there. And the water recharges on the edge of it, and it discharges in springs in Queensland over here somewhere, and in South Australia at the Dalhousie Springs. That's quite a spectacular place. If you've ever been there, it's worth a visit. Other prominent aquifers, you notice these in Central Australia, central part of the territory. There's a fossil drainage network. We call them paleo valleys, and they date anything from 5 to 40 million years old, when it was much wetter. And they actually flow, or they terminate inland, these ones, at lakes in Western Australia. Actually, there's a whole system of these right at this latitude, right across Western Australia and the NT. It's you can see them on satellite images. It's an amazing thing. But they contain groundwater, usually at the bottom of the channels. They're just river channels, really, and there's gravels at the bottom of them. Right, but associated with them are sedimentary basins like the Tea Tree Basin, which is, you pass it at Tea Tree on the Stuart Highway, and a few others. And they were sort of created tectonically, where areas were actively being deformed downwards, and sediment was pouring in, but the water seemed to have overflowed and flowed elsewhere. There was basically runoff from the Central Highlands into those, and then off along those drainage channels. So one big thing, climate has a big effect on the regional aspects of groundwater, especially rainfall, especially this prominent north to south zonation from high rainfall in the north to low in the south. People often talk about, well, divided into two zones. Talk about the humid zone in the north, which is the area affected by monsoon rains, where you get fairly regular rainfall each year and a lot heavier rain. And then the arid zone in the south, where rainfall is more sporadic and in total less. So there we have the humid zone. Well, I just described that then, and the arid zone. So that's just a convenient way to discuss the aspects of groundwater. I'll tell you the differences between the two. So let's look at water quality. Here I've picked total dissolved solids, which is groundwater salinity. the colours of these are measurements made in boreholes. When they drill the hole, they often measure the TDS. So the blue ones are low salinity and the red are higher salinity. I don't know, I hope you can see it. You can see a definite gradation going from fresher water in the north. And then as you go down the colour changes, so it's getting saltier. And then in the arid zone, it's dominantly more than 1,000 milligrams per litre. But you get fresher water interspersed with it in special situations, you know, like shallow aquifers along rivers where recharge can happen easily. You get fresh water, you know, like say something like the Todd River in the town of Alice. There's a small alluvial groundwater basin under that, and you'll get fresh water close to the river, because it's only a shallow aquifer. So you might ask, why does the salinity increase in the arid zone? It's all to do with every rainfall event, or in order to recharge an aquifer, the soil has to be fully saturated. Otherwise, the rainfall will just go to filling up the soil zone. But once it's fully saturated, then it can move down deeper and recharge the aquifer. But in the arid zone, big rainfall events that could recharge the aquifer are few and far between. You might get small rainfall events, and the water just goes into the soil. But all rainfall contains minute amounts of salt, you know, derived from the ocean. They're only minute, but it's important over a geological timescale. So while it's sitting in the water, if it's within ET range or just capillaries zone where the water can evaporate, your salt will be left behind. And until you get a big rainfall to flush it down, the salt just accumulates. So in the arid zone, more salt, it's easier for salt to accumulate in the soil zone. And that's the main reason for that. Whereas in the humid zone, with the regular rainfall we get, the salt just doesn't get an opportunity to concentrate by evaporation in the soil. So now recharge. In the humid zone, you've got that diffuse recharge. That's the dominant type of recharge. But it's not to say the other type, like local, you can't get localised, which you can, but diffuse is the dominant. And just looking at when the monsoon arrives, that's sort of a typical satellite image when it's here. You can understand why you get diffuse recharge, because often it's raining over large areas and probably heavy rain too. So in the arid zone, the recharge is more of the type where it's concentrated by rivers. And here's an example of where that can happen. This is just west of Yuendamu, and these finger-like features going north, these are termed floodouts, and what they are just streams that originate in the hills in the southern part of the image, where all the rainfall gets concentrated into the channel, and then when there's a big event, it'll flood out onto the sand plains to the north. And if there's enough water, they're an important source of recharge, but it's a fairly local thing. Now, These are measurements of groundwater levels made in boreholes. The blue ones from the humid zone, a typical humid zone one, and the red one's an arid zone one, just to show you the difference. You notice with the blue one from the humid zone, there's a definite annual signature. It goes up in the wet season and then gradually declines in the dry season. You know, if it's a bad year, it might be a smaller rise, but generally there's an annual signature. Whereas in the arid zone, you can see the peaks on the graph. They're the recharge events. They can be decades apart. You see the big peak here in the 70s, that was a very prominent rainfall event in the early to mid 70s. And all of these hydrographs were shot up, and they took years to go back to the normal level, if indeed they have. Well, in this case, they haven't. This one's from Ali Karang. It's got quite a long record, but see, in the 60s, the levels were just above 20. Or sorry, no, it's 14 on that scale. But if these two events hadn't have happened, the water would have declined on this path, and it probably wouldn't be back to 60s level by now. So that was a massive event. This one, I'm just interested in this. It's not completely relevant, but this is a GRACE data from a GRACE NASA satellite, which measures gravity. It goes around the Earth and measures gravity. But it's so sensitive, it can measure changes in the storage of water on and below the ground. And that's what these graphs are. And you can see the same sort of annual, they're similar to the bore hydrographs. And you can actually, on a broad scale, you can estimate the volumes that it's either gained or lost. So I think that's quite an amazing thing, that people can do that. What we got now, residence times. Well, in the top end, you're looking at sort of up to hundreds of years residence time. That means the time it takes from when it goes in to when it leaves the aquifer. Whereas in the arid zone, it's much longer. I can't see the figures there, but you know, hundreds to millions of years in general. Now, discharge. In the top end, springs and it's a bit hard to read. Yes, springs and stream bed discharges. They're sort of similar thing. It's just that one's under the water. They're the main form of discharge. In the arid zone, you've got the ET from things like red gums along riverbeds and salt lakes. Salt lakes, a lot of them are actually groundwater discharge zones, even though you may not see water in the lakes unless it's rainfall. The water table under these lakes is fairly shallow. It's within the capillary zone, and water's constantly evaporating and leaving the salt behind. That's how they form. And so springs, you can see the huge difference in distribution of springs, the humid zone to the arid zone. Topography's got a little bit to do with it, but it's also that there's not as much water going in, so not as much comes out, so there's less springs. Springs can be beautiful things like this one at Mataranka, or they can just be muddy little seeps. But some of the, especially the ones that come out of the karstic aquifers, can be wonderful things. And this just shows you the extent of groundwater discharge into streams either by springs or seepage into the beds, all the streams that are coloured, they've got permanent flow even at the end of the dry season. So you can see it's quite extensive in the top end. But a lot of the ones that don't flow at the end of the dry season, they may flow. There's lots of them that flow for variable amounts of time during the dry. You know, it might only be for a month after the wet finishes, or it might be 6 months. So anyway, so that things like that support wonderful ecosystems along them in the otherwise, that's typical vegetation along a spring-fed river. This one's the Wickham River in the VRD, so that's spring-fed, and you can see the difference in vegetation, the river and vegetation compared with the sort of dryish-looking woodland. Even in the arid zone, you can get that happening. This is Palm Valley, where you get really unusual vegetation and actually some standing water. That's all groundwater seepage. So use, I'll just flick through these. There's different uses, urban and industrial, tourism and community, pastoral, mining, and these are the communities and towns. Darwin gets 20% of its water from groundwater, Catherine 40%, Tennant Creek and Alice Springs are completely dependent on groundwater. So, or to sum up really, I think groundwater is a wondrous part of the NT environment, even though you can't see it, because it's so widespread and it's virtually everywhere under your feet, but we're not aware of it usually. And it's so interrelated to ecosystems, rivers, things like that. It's just an amazing feature. So I hope I've convinced you that it is. Thank you very much.
Thank you, Stephen. That was awesome.
Good.
So we have a little bit of time for questions from people both here in the room as well as online. Yeah, maybe 10, 15 minutes, something like that.
Yep.
Does anyone have any questions, either in person or online?
I've got a two-part question. I actually wasn't aware that the aquifers were so big. So for an example, if I guess, mining or certain operations where pollutants are going into the groundwater, does that have the potential to spread across like the whole aquifer?
Well, eventually, eventually, the best thing would be to avoid it in the first place, to avoid spills. And groundwater moves very slowly. Usually it's like centimetres per year, say in arid areas, but places like near, when you get close to a spring, it's like pulling the plug out of your bathtub. The water's virtually flat a long way away from it, so there's not much head driving it, but when you get close to the plug hole, it's steeper. So the speed is governed by the gradient of the water table.
And then my second part of that question is you're showing usage of groundwater, if it's commercial or whatever it may be.
Yeah.
Is there enough recharge to compensate usage? So is there like a negative relationship with water levels for usage, or is there enough recharge to counteract that?
Well, in some places like Alice Springs, town water supply, that's actually mining the water because there's no choice really, otherwise the town wouldn't be there. So that's mining, but elsewhere in general, you try and avoid that. you have rules in place, licensing of water now. And that's and management plans, and that's to avoid that sort of thing.
You're the chair, you go ahead.
Yeah.
Okay, well, Kamal put her hand up first.
Yeah.
You missed it by a second, sorry. Okay, now we'll go to an online question.
Thanks. Thank you. Beautiful presentation for a person like me who doesn't work on groundwater. So it's really good to know. Thank you so much.
Thank you.
It is a wonderful place to be.
Good.
So my question is just following on that. So we got like those contesting land uses, especially in the regional basin, both agriculture and mining. So how do you see that, because if we're going for mining, especially fracking, so it's going to have a significant impact on, how do you see that? Like I'm just,
Well, if
if
it's
you plug,
yeah,
take the plug out of me.
where you have big uses, it has to be managed to within the sustainable limits. And
I mean, I question that thing. We always call that manage, and we forward the risk. So if we mess that up, and the chances could be that in those big operations there will be spills and the type of chemicals they use for fracking, aren't we messing up the whole system? I mean, I wonder.
well, I'm not an advocate for the gas industry, but where the gas is, where they're doing the fracking is like depths at 1.5 to 2 kilometres, but the aquifer that's people are worried about is sort of the top, a couple of 100 metres, and they're supposed to, the wells, they have multiple layers of steel casing and cement to avoid them being connected. And theoretically, if they stick to all those guidelines or rules, it shouldn't pollute it, even though you look at other places in the world where it has. So it's a matter of strict control of it, I think.
Okay.
I was really interested in with the satellite data, how stable the water volumes looked over time. I'd love to have seen it over a longer period and right up to today. But in my ignorance as a biologist, seeing that that almost even split between ice and snow and groundwater, I wonder, I don't know when that data is from, but I would have assumed that with ice and snow melt, that's changing. And not only is it changing with sea level rising, you've got more sea surface area for evaporation, and therefore in theory more rain, and therefore there should be more groundwater at a global level. So I wonder how quickly that ratio is changing and what that graph actually looks like globally of groundwater.
Well, actually, they've got a nice little app on the Grace, and you can generate your own. I don't know the answer to your question, but you can generate your own graphs, whichever area, and no matter how large. That's a pretty interesting thing too. But their data, it only goes back, I think, 10 or 15 years. That's when they put the satellites up.
You had it to
hopefully they're going to put up or new ones that are much more sensitive. Now, you've got pixel sizes of hundreds of kilometres, so it's pretty rough.
But you don't know if groundwater is increasing.
Well, in that territory, rainfall's definitely increased. After that big event in the 70s, water levels or in rainfall itself in general is greater, so levels are higher, or in the top end. I think it's more or less even in the bottom end, arid zone. So, I presume that's something to do with climate change.
Okay, thanks.
But ice and snow aren't a big effect in the territory.
Hannah, do we have any online questions? I don't want to ignore our online friends.
There's quite a few online. We might not be able to get to all of them, but this is one from Nicole. She would like to know if we want to measure impacts to groundwater, what scale is relevant? Do we know what scale to consider?
I didn't hear that.
Sorry. If we want to know, if we want to measure impacts to groundwater, what scale is relevant or what scale should we consider?
Well, I suppose it depends on what your purpose is. If you're looking at, say, the Berry Springs aquifer, that's only a small area, you'd look at that size, but yeah. So it depends on what your purpose is. If you were looking to contribution of groundwater to rivers on a regional scale, then you'd have to look at a much bigger area.
Anyone? Sure.
Another online one.
Sure.
Yeah. This is one from Billy. She is wondering, with the massive Cambrian limestone aquifer, what tens of thousands of Territorians rely on? How localized would pollution spread if it was contaminated? What quantity of pollution could be catastrophic?
Well, yeah, it's a bit hard to say. Probably it'd go fairly slowly, as I said, because in the areas where they're working, if that did happen, the gradients are very low, so it'd only be, like centimetres a year. Even if there's large cavities, the gradient of the water table is the key thing. That's what drives the speed. But eventually, in the long term, it'd keep going from south to north. That's the general direction it flows in the area where they're doing the gas work.
I'm not sure how we're doing on time. Trustee, I think you had it.
Yeah.
4 minutes.
Okay, the question, first of all, is thank you very much for your presentation, was very clear. And so you mentioned there is 3 types of aquifer in NT. So I was wondering which one is the more productive, but also which one have the more potential of water supply. So I guess the answer is cars, the carbonate, but I wanted to confirm first. So that's the answer. The carbonate are the more with higher potential.
You asked and answered.
I have another question related to that because, as you know, the carbonates, if they are karstified, depending on the degree of karstification, the recharge from the surface water into the groundwater get faster and faster. So this is something good if you want to recharge the aquifer, but it's also risky because if there is any pollution on the top, this pollution can get very quickly to the groundwater. So my question was, what is NT doing action? What are the actions NT is doing to protect this highly sensitive groundwater resource?
Well, the actions are the rules in place for how they construct their boreholes or the gas wells.
Okay.
That's the main way, and also storage, how they store the chemicals at the surface in case there's some sort of spill. That's probably
because there are different. Well, there is agriculture in NT happening. There is cattle, maybe fracking. Mining, so I don't know, it depends where it's located because the aquifer, the cars, they are not everywhere, but in the areas where the aquifer is located, there are potentially activities which can pollute the water. So it was like, what is the management, what are the actions, because it's very important, the groundwater, as I can see.
That's true. And the thing is, once pollution's in the water, it's very, very difficult to remove it.
Yeah, I know that. Very expensive.
Yeah.
So we probably have time for one more question. I think gentleman in the back.
There's been a lot of concern about pollution of aquifers through fracking.
Yes.
I'm much more worried about the large number and the, as you've described, the fracking holes are a long way away from the aquifer. I've been much more worried about the large number of uncapped pools open to the environment that are no longer in use.
Yes.
And there's thousands of them. Well, I think there's thousands of them, not, just open to the environment, straight down to the aquifer.
That's true. In the past, there were no rules about decommissioning them, filling them in properly. But nowadays, you have to do that. But it's true, there are a lot of old ones from the old days.
You're right.
Yes. Often they'll weld a cap onto them. But, So, yes, even stock bores, it's mainly stock use.
Yeah, some people's a big problem.
In the areas where they frack, and a lot of them were never constructed to standards because they're old. They don't have proper cement caps.
Casey driving.
Yes.
Directly open to the environment.
But luckily these days, if you do a new one, you have to construct them to those standards, and you have to decommission bores properly.
There'd still be thousands though.
Well, possibly, yeah. It's a big place. Yeah.
So there may be more questions out there, but we've kind of run out of time. And I apologize to those people who wanted to ask questions, but yeah. But thank you, Stephen, for coming here and talking to us today. It's been a great pleasure, and
I think you go.
yeah,
It's been my
and,
pleasure to speak to you.
and so I do have a few.
I can answer questions
Oh.
over a cup of tea if you like.
Yes.
As long as it's not about fracking.
But thanks to all the people who helped today, including Hannah, Zach, and Will, and also the Northern Institute for allowing us to use this room. And for everyone attending in person and online. And we'll soon head over to Yellow 2 for morning tea. All of you are welcome to join us for some cakes and carbs. All right, thanks, everyone.